So currently we know about friction. Friction is just another force in our list of forces, right? FF, Fn, Fg or Fw, Ft, and F spring if we want to differentiate, and then some other F push or pull that we haven't taken into account just due to some kind of contact. Okay, so we know these are our possible forces that we can identify on a body. So I want to talk about the value of the force of friction. So let's just think about, for example, let's have a box of Girl Scout cookies. So these are cookies. That doesn't really look like a cookie, but anyway, on a ramp, and it's just sitting there, right? And it's not going anywhere. So we know, we know what forces are on this box of Girl Scout cookies. So we can draw a free body diagram. We know that there's a normal force because it's sitting on a surface, and the normal force is perpendicular to the surface of contact. We know there's gravitational force pulling it straight down. So that's the normal force, of the gravitational force. There's no rope attached to it. There's no spring attached to it. There's no hand pushing it. And is there a frictional force? We know there must be a frictional force because it's sitting still. We said that. I didn't write it down. I can just write V equals 0. And so we know there must be a frictional force holding it up. And it doesn't matter where you draw the frictional force, but I tend to draw it, near the surfaces. It's frictional force, we've defined already, is the force resisting motion between two surfaces, and it's parallel to the surfaces in contact. So we've defined this previously. Let me remind you, I'll say that one more time. The frictional force is the force that resists motion between two objects, and it's parallel to the two surfaces of contact, as opposed to the normal force, which is due to an object sitting on a surface, which is perpendicular to the two forces. So actually FF and Fn are always perpendicular to each other. That's an interesting thing to know. But anyway, so we know there's a frictional force, but now we're going to spend some time talking about the value of that frictional force. So for example, in the example shown, what is the value of the frictional force? You can't give me a number, but the frictional force, because V equals 0, must just be balancing the downhill forces, right? So there are forces trying to pull this thing downhill, and the frictional force must be balancing them. These are not forces you would put on the free body diagram, because the free body diagram is a picture of all the forces. If I started adding the downhill forces, we would just be duplicating, right? Because what is the downhill force? The force pulling the box of Girl Scout cookies down the hill is the gravitational component. So if I were to draw that in here, now I've duplicated that because I've duplicated the gravitational force, because this is a component of the gravitational force. It doesn't belong in the free body diagram. But I can draw a diagram, and I can draw another picture. So this is my free body diagram. This is my diagram or picture. And let me just draw another picture, of the Girl Scout cookies. And that was a terrible picture, but anyway, we know that if I want to look at the gravitational force is straight down, and it's got a component down the hill and a component perpendicular to the hill. So this is Fg, let's just call down the hill the x direction, plus x, and perpendicular to the hill the y direction, plus y, just defining my directions. And so this is Fgx, and this is Fgy. Right, so the down... Okay, I redrew it. And we could, again, this is not quantitative, I'm just saying, what must the frictional force be? Well, the thing trying to pull the box of Girl Scout cookies down the hill is Fgx, so therefore Ff must equal Fgx because it's not going anywhere, so the force is balanced. Or, we could say F net equals ma down the hill. Okay, there we go. I solved it like a Newton's second law problem. F net x equals ma. We identify the net force in the x direction from the free body diagram. We identify the acceleration as 0 because we know the velocity equals 0. And so therefore we can conclude that Fgx must equal Ff, the frictional force. Okay, so that's a Newton's second law problem. We've done plenty of those. But let's look a little bit into the nature of friction. Just so we don't have to deal with components or anything, just to look at the nature of friction, let's just imagine our box of Girl Scout cookies on a flat floor. Okay, or table, flat table. And let's imagine that I push on that box of Girl Scout cookies, I simply give it a push, right, with my hand. We'll just call that a push. And let's say the box of Girl Scout cookies doesn't go anywhere. It doesn't go anywhere. So why doesn't it go anywhere? Just hit pause thinking that would give you time to think, but that's silly. That will not give you time to think. Why doesn't it go anywhere? It doesn't go anywhere. If I'd say it doesn't go anywhere, right? V equals 0, it doesn't go anywhere. Therefore, there must be a frictional force back on it, right? And we'll just say FF, frictional force back on it. Is the value of that frictional force? Since V equals 0, we could go through a Newton's second law analysis, but we find that the frictional force equals F push. Okay, so let's just say that that my initial push is 5 newtons. I'm just telling you, 5 newtons. So now let's say that I increase the push to 10 newtons. So theoretically, we're just going to draw a longer vector here, but it still doesn't move. So what can you say about the frictional force? The frictional force must react to that, right? The frictional force must still be equal to the pushing force if it doesn't move. So the frictional force is now 10 newtons. See, the frictional force reacts to the force that you exert on the object. Let's say I push with 15 newtons and it doesn't move. Then what? The frictional force must get bigger, right? So the frictional force is continually going to equal and opposite the pushing force until what? Until I push hard enough to get it moving. So what that tells me is that there is some maximum frictional force. And if I push hard enough, obviously if I push hard enough, I'm going to get this box moving, this box of cookies moving. So the frictional force must always be equal and opposite to the force that I'm pushing with, that I'm trying to move the object with, if it's not moving until I get it moving. So we can write that in equation form. So it's a pretty simple equation, just that the frictional force when an object is not moving, and I didn't write that, but I'm saying that, is less than or equal to some maximum. Now, so when an object is not moving, that's a special kind of friction, right? The object is static, it's called static friction. FFS is less than or equal to some maximum. FF static, right? FF static, which is abbreviated FFS. So that's static friction. Static friction is less than or equal to some maximum. And we call that maximum, lots of subscripts, FFS max. We define that maximum as FFS max. If we overcome that maximum static frictional force, we will get the object moving. But until then, the static frictional force is going to be less than or equal to that maximum. And the only way we can know what the static frictional force is to do a Newton's second law analysis on the body, right? That the forces must balance. Look at that maximum value. Let's see what we can say about the maximum value, FFS max. We can do some experiments and we can find that lo and behold, we find, and this is experimental result, turns out that FFS max is proportional to the normal force. Not the weight, but the normal force, which might be equal to the weight, but it's proportional to the normal force. In other words, if I push down, right, if I stand on this box, let me stand on top of the box of Girl Scout cookies, I'm not sure why you'd want to do that, then FFS max is bigger, because there's a bigger normal force on the bottom of this box. It's harder to get it moving. Not because of my weight, but because the normal force is bigger. Okay, FFS max is proportional to the normal force. That's just observation. That's empirical. And the proportionality constant is called the coefficient of friction. The proportionality constant is called the coefficient of friction. And because this is static friction, we'll say it's the coefficient of static friction, because we will differentiate that from other kinds of friction. So the coefficient of static friction, and we call it the Greek letter mu. This is the Greek letter mu, like what a cat says, mu, right? Or, well, cats say meow, but anyway. In equation form, we can write this down. That the static frictional force must be always less or equal to some maximum, and that maximum is equal to mu sub s times Fn. What is this mu sub s? We'll talk more about it later, but the mu sub s is just a proportionality constant that has to do with, what do you think it has to do with? I paused the video thinking that gives you time to think, but it has to do with the properties of the two surfaces in contact. Coefficient of friction in general has to do with the properties of the two surfaces in contact. So for instance, right, you know, your rubber tires on a asphalt road, they're hard to slide against each other, right, because you want your car to stick to the road, whereas ice skates on ice slip easily. So metal on ice has a much lower coefficient of friction than rubber on asphalt. Right? So we'll talk about those coefficients of friction another time, but that's just the proportionality constant. So we don't have an equation for FFS because it's less than or equal to some maximum, but we do have an equation for FFS max, which is nice, right? So we've actually got an equation we can plug into our Newton's second law, which gives us more information if we know we're at the maximum. If we're less than the maximum, then we can't. But once we get a body moving, so now let's say take our box of Girl Scout cookies and we're exerting some kind of push on it and it's moving now, V is not equal to 0. It is no longer static friction. It is no longer static friction. It is now called kinetic friction. There's still friction, right? There's still a resistive force because we're still sliding against the ground, but it's called kinetic friction. And this is the important thing about kinetic friction, is that kinetic friction is not dependent on how hard you push, right? It's not dependent on that. It turns out that kinetic friction, FFK, is also proportional to Fn, with a proportionality constant called mu sub k, coefficient of static kinetic. So first of all, let me say that again. The kinetic friction is not dependent on how hard you push on it, whereas the static friction was up to a maximum. But not only that, think about your experiences pushing heavy objects. I'm sure you've pushed something heavy at some point. When you're pushing something heavy, in particular, think like a file cabinet or a bed, it can be hard to get the body moving. But once it's moving, it's easier to move, right? In general, it is true that FFK is always less than, must be less than, the maximum static frictional force. It's always easier to slide a body along a surface than it is to get a body moving. And actually, if this wasn't true, it would actually mean we could never get bodies moving, which doesn't make sense. If you think it through, it would mean we could never get bodies moving if this wasn't true. But this is true, which tells us that, therefore, mu sub k is always less than mu sub s. The coefficient of kinetic friction is always less than the coefficient of static friction because the coefficient of the kinetic frictional force is proportional to the normal force and the maximum static frictional force is proportional to the normal force. Since FFK is always less than FFS max, then mu k must be less than mu s. Quickly, just address one more thing, which is just to understand the nature of friction. Friction is a little bit tricky in terms of science because it's a little messy, right? Why do you have friction between two surfaces? Why is there friction between two surfaces? And the answer is because surfaces are not perfectly flat. The answer is really that surfaces are bumpy, right? So imagine that's microscopically bumpy, right? Surfaces are microscopically bumpy. So those, like your fingers, it's hard for me to... Sorry, I want to talk about interlocked fingers, but it's hard for me to do that because I can't draw pictures of hands and I can't show you what I'm doing. But if you interlock your fingers, it's hard to move your hands, right? That's what happens to these bumps. These bumps become interlocked, right? You put an object down on top of another object. They look perfectly flat, but microscopically they're not, and the atoms become interlocked. So if you try to push one, they're in the way of each other, and you've got to either break them off or push it so it rolls over the next atom or molecule, right? So there is a roughness. So that coefficient of friction has to do with the tendency for a particular kind of surface, right? Wood has a different kind of roughness than a metal, than different kinds of metal, than asphalt, etc. The rougher the surface, the rougher microscopically or macroscopically, the more friction, the higher the coefficient of friction. Okay, have a wonderful day. I wanted a matchstick puzzle. Okay, here's a matchstick puzzle. Move just one stick to make this equation correct. Go ahead and pause and try to figure it out. Move one stick to make this equation correct. Now, there's a trivial answer, and then there's the real answer, right? The trivial answer is you can take any one stick from any of the numbers really, and you can go ahead and just move it over the equal sign and make it not equals. That's the trivial answer. I think there's only one other answer. You can pause it, but here's the answer. You take this stick here, and you move it to here. Right? So what you get is, ta-da, did you get that?